Hey everyone, and welcome to The Explainer. I am so pumped you're here today because we're looking at something that honestly affects almost every single one of us, yet it somehow manages to stay completely invisible. Today we're going to explore the absolutely fascinating, massive, and very physical reality behind the seemingly magical world of artificial intelligence. So just think about your own workflow for a second. You type a prompt and instantly, boom, a perfect answer just materializes. It feels completely weightless, right? Like it's just delivered straight from the magical ether of the cloud. But what if I told you that simple, weightless generation actually requires massive power plants, industrial cooling, and acres of specialized silicon? Look, if you don't know the physical journey of your data, you are missing out on literally one of the biggest infrastructure shifts of our lifetimes. All right, let's dive right into this. First things first, we need to completely shatter this illusion of the cloud. I mean, the cloud is a brilliant marketing metaphor, but it's not an actual location, and it certainly isn't floating up in the sky. It is plugged in. AI is absolutely made of clever software and code for sure, but software cannot think without hardware. Every single time an AI system processes your request, it's triggering this massive, heavy industrial machine that's operating right under our noses.
Section 1. Inside the AI machine. To really wrap our heads around this physical loop, let's look at what actually happens the exact second you hit send on that prompt. Picture this like an enormous, highly advanced industrial kitchen. Your prompt travels through the internet to a data center, where specialized chips, acting as our incredibly fast cooks, instantly begin billions of parallel mathematical calculations. But running thousands of digital ovens at once creates intense heat. Massive cooling systems, like giant chillers and liquid pipes, have to work continuously just to carry that heat away. And the whole shebang is fed by a massive draw from the local power grid.
And here is the absolute craziest physical reality of this whole setup. Every calculation ends as heat. AI doesn't just need chips, it desperately needs somewhere for the heat to go. Because AI processors pack way more computing power into a single server rack than traditional hardware, the thermal load is just astonishing. So your AI answer actually depends on this constant, unbroken loop. Electricity creates computation, computation creates heat, heat requires cooling, and well, cooling requires even more electricity.
Section 2. The massive energy scale.
Okay, so that wild physical loop we just talked about, that happens for one single request. Just one. But multiply that by millions of automated agents and global video generations happening every single second, and we reach a staggering number. According to the International Energy Agency, global data centers consumed about 485 terawatt-hours of electricity in 2025. By 2030, their central projections suggest that could reach 950 terawatt-hours, which is roughly 3% of all global electricity demand. And the energy used specifically by AI? Yeah, that is projected to triple. And this massive infrastructure is growing at an absolute breakneck pace, right in our own backyards. Based on data from the Lawrence Berkeley National Laboratory, the 2023 baseline for all U.S. data centers was about 176 terawatt-hours. But by 2030, that projection shoots up to 649 terawatt-hours in their reference case. To put that into perspective, that means data centers could soon consume nearly 12% of all U.S. electricity. This isn't just some background software update we're talking about. This is a fundamental reshaping of our power grid.
But here's where it gets super practical for our actual communities. 3 or 12% globally or nationally might not sound like the end of the world. But remember, data centers are not spread evenly across the Earth. They're heavily clustered in very specific regions. And because these massive facilities require firm 24/7 power, a small global percentage can quickly morph into a very large local problem. When several giant data centers arrive in one area, way faster than a region can build new power plants and grid connections, it puts intense pressure on local transmission lines and substations. It really becomes an issue of having enough power in the exact right place at the exact right time.
Section 3. The efficiency twist. Now, before you go assuming this is just some doomed story of runaway energy waste, we have to talk about the tension between incredibly fast demand growth and incredibly fast efficiency improvements. Engineers measure this using a really smart framework called Power Usage Effectiveness, or PUE. It's basically a simple ratio. You take the total energy used by the facility, including all those massive liquid cooling systems and the lights, and divide it by the energy used directly by the actual computing equipment. A score of 1.0 is mathematically perfect. That means zero energy is wasted on overhead. So the closer to 1, the better. And you know what? The industry is getting remarkably good at this. For example, Google recently reported a fleet-wide PUE of just 1.09 for 2025. That means very little energy is actually being lost to facility overhead. Even better, they've achieved more than 3 times the computing performance per unit of energy compared to just 5 years ago. Better chips, smarter software, more efficient cooling, it all means that the exact same amount of electricity is buying us significantly more artificial intelligence today than it did yesterday. But because of these wild variations in efficiency, there is literally no honest universal conversion that says one AI prompt equals exactly this much electricity or water. Actually, a Berkeley lab review found that water use can vary by more than 10,000-fold, depending on the servers, the climate, and the grid. So whenever you hear dramatic claims in the media about AI's footprint, you now have the tools to ask these 4 absolutely crucial questions. Number 1, what is actually being measured? Is it one model or all global data centers? 2, is this number measured from the past or projected into some uncertain future? 3, what sits inside the boundary? Are they just counting the chips or the cooling and grid generation too? And 4, where and when does the electricity come from? Because a prompt run on solar power in a cool climate is vastly different from one run on coal in the middle of a desert.
Section 4. How AI helps the grid. Which brings us to a really fascinating bonus insight. We've talked a lot about what AI takes from our power grids, but there is an entirely unexpected two-way relationship emerging here. While AI absolutely increases energy load and demands all this new physical grid infrastructure, those exact same AI models are now being deployed as grid solutions. AI is uniquely good at processing vast amounts of data, right? Well, it's currently being used to drastically improve weather and renewable generation forecasts, instantly detect grid faults, and even help grid operators route power more effectively across the transmission lines we already have. Just to give you a sense of that potential scale, the International Energy Agency actually modeled a widespread adoption scenario where AI tools could potentially unlock up to 175 gigawatts of additional transmission capacity from existing lines. Now, it's a modeled opportunity, not a guarantee, but it reveals an incredible loop. AI increases electricity demand while simultaneously acting as the intelligence needed to help the grid operate more efficiently to actually meet that demand. So the crucial point here is that we really need to shift our mindset. The best question to ask isn't simply, does AI use electricity? Because of course it does. Every digital service does. The real economic and societal question we should be asking is, how much valuable work can AI deliver for each unit of energy and infrastructure it consumes? We shouldn't just look at energy consumption in isolated panic. We need to evaluate the actual value produced against the physical cost. Which brings us to our final takeaway today. Once you really understand this journey from your phone to the internet to the specialized chips, the cooling towers, the substations, and the power plants, you realize that AI is not merely a new kind of software. It's a massive, fast-growing physical infrastructure industry. After seeing this incredible power chain, the cloud is truly never going to look weightless again. We know electricity powers the whole system, but it's actually the highly specialized hardware that dictates just how much intelligence that electricity can actually buy, which leaves us with a massive geopolitical question. Why are the most powerful countries and companies on Earth in an absolute all-out race to control the tiny pieces of silicon at the very center of this boom? Now that is a fascinating story, and it's exactly what we're going to be covering in our next explainer. Thank you so much for joining me. Keep asking great questions, and I'll see you next time.
Thanks for staying to the end. If this helped, we'd really appreciate a like. It helps us make more videos like this for you. Want to stay ahead? Get Market Lens by CXProWealth, AI-powered insights delivered to your inbox to help protect and grow your money. Don't miss out.